Alrighty, well that's it for the photoelectric effect. And I want you to see the photoelectric effect is proof that light is not just a wave, it's also a particle. I'm going to give you another proof that light is not just a wave, but it's also a particle, and that's the Compton effect. Oh, by the way, Albert Einstein, he won a Nobel Prize for what he discovered about the photoelectric effect. He did not win his Nobel Prize for relativity. He won it for the photoelectric effect. Interesting. Yeah. Okay. The Compton effect. And photon momentum. When a wave travels from one medium to another, let's say I'm a sound wave, I'm listening to some music, and that music travels from the air into the water. V, F, and lambda, which changes and which stays the same? When this sound goes from air to water, what changes and what stays the same? Between V, F, and lambda.
Velocity change.
Yeah, Trevor.
Does velocity change?
Sure, the velocity changes because sound. How does sound travel in water? Faster or slower?
Faster.
Water's, yeah, sound is faster in water. So the speed goes up. Tell me, what else changes? Yeah, lambda. If the speed goes up, what happens to lambda? I'll tell you what, it goes up because what happens to the frequency? It stays the same. And so we get used to that fact that frequency is inviolate, right? That is, when a wave goes from one medium to another medium, speed can change, wavelength can change, but that frequency is not going to change. Celine Dion's not going to sound like Barry White, okay, just because you're underwater. She still sounds like Celine Dion. The frequency doesn't change. And we're used to that being true for light in all interactions. Light maintains its frequency, okay? But then comes the Compton effect, and let me show you what happens with the Compton effect. Okay? Here, you've got an electron at rest, and you hit this electron with an X-ray, what they call the incident X-ray. And then after the X-ray hits the electron, bam, the electron has acquired some speed. The electron is now going in motion. And this X-ray has been diverted in its path. The name for this electron, we call it the recoil electron. It got hit and now it's like recoiling from its, collision. And this X-ray here after the collision is called the scattered X-ray. And here's the weird thing about the Compton effect. The frequency of the X-ray changes, something that doesn't happen ordinarily. But I've got a photon that collides with an electron and then it becomes a photon of a different frequency. This photon has a frequency equal to F, and this guy has a different frequency equal to F prime. You tell me, do you think the frequency went up or do you think it went down? Good, it went down. Because do you think it gained energy or lost energy after this collision? Good, it lost energy. And where did that lost energy get transferred to? Yeah, to the electron, to give that electron kinetic energy, okay? it turns out, and I'm not gonna get into this, but you get a conservation of energy situation. Oh, I might as well write it down. You know, you get conservation of energy. Where the initial energy of the system, which is just the energy of this X-ray photon and the energy of the electron at rest, ends up equaling the final energy, which is the energy of the scattered X-ray, or the scattered photon, plus the kinetic energy of the electron. And I do want to make, yes, Jim?
Electron at rest, that's pretty cool.
That's right.
Are there ever electrons at rest?
I don't know. You know, that's a really good question. Yeah, when you put an electron on an insulator, but I mean, as far as how they did this actual experiment, how did they get this electron to be at rest, or this group of electrons to be at rest? I don't know. I'd have to look it up. It's called the Compton effect, so he did an experiment involving this. But Joel, I'm embarrassed to say I'm ignorant. I don't know how they got it to be an electron at rest. Isn't that weird? Yeah. Or maybe it's actually, maybe this is a simplified high school version. Maybe it's a bunch of electrons that are in motion, but then you get to see it diverted from its motion because of the collision. I don't actually know. I'm so ignorant. So all you YouTube visitors, don't watch me, except if you're in my class. Okay, great. So there you go. And I want to make sure you know that the frequency of the incident X-ray is going to be bigger than the frequency of the scattered X-ray, right? I mean, it's got to give up some of its energy, and in so doing, it's going to get a reduction in frequency. Okay? Well, another thing is going to get to the water. Another thing is conserved in this collision, and that's conservation of momentum. But here's the weird thing. How can an X-ray have momentum? How can a photon with no mass, just pure energy, have momentum? Well, it turns out it does, because when you use this formula for photon momentum, you get the conservation of momentum totally working. And here comes the momentum of a photon. The momentum of the photon ends up being h over lambda. And so when you do conservation of momentum now, it works out just well. Here, let me see. Do I have an example? Okay. Look at example number 2. An X-ray. Oh, maybe we should answer the questions. Okay, let's answer the questions. Compton effect and momentum of photon. I'm looking at your sheet now. Arthur Compton in 1923 discovered that when he moved the rest of the X-ray at frequency F, the electron would acquire momentum. Now it's called the, what do we call that new electron that's not in motion?
The recoil electron.
Yeah, recoil electron. And a scattered X-ray photon would have a different. Good, write that down. Number 2, yes? Let's just put on the class. Thank you. Number 2, he found that if he treated this as any collision, momentum would always be conserved as long as the momentum of the photon was defined as momentum equals h over lambda. By the way, what is h again? Yeah, Planck's constant, Max Planck. Both the photoelectric effect and the Compton effect show that light exhibits what kind of behavior? Yeah, particle behavior. Because only particles get to have momentum. Light doesn't have momentum, does it? Yeah, it does. So we're treating it like a particle. And so now, I'd like everyone to please do example 2.